In this video, we're going to work another example problem that has to do with approximations of trig functions. We're just going to do a simple word problem, and the idea of this is we're wanting to illustrate the fact that for real-world problems, to solve real-world problems, we have to be able to just be given an angle, and we need to find what the trig function value of that angle is with no other information. So in the previous problems, in the previous sections up to this section, we were evaluating trig functions just to learn about the definition of trig functions, but we were given certain side lengths like coordinates of a point, and so we had some information to where we could solve for the trig function values. Well, in real life scenarios, you don't have that extra information. You just need to find what the trig function value of an angle is. And so we could actually solve for exact values of trig functions if we had a special angle, 30, 60, or 45 degrees, or if the reference angle was one of these special angles. But for other angles, we can't find exact values, so we need to do approximations. We need to use the trig function definition and then do like a numerical method to get as accurate as possible of an approximation for that trig function value. And so that's what we do, but we let mathematicians or professionals set up the numerical codes, and we just go pull the values out of our calculator. And so that's what we're going to illustrate here. We're going to we're not really illustrating how it's done numerically, but we're just going to illustrate a real-world problem where we're going to have an angle here, and we just need to plug it into a trig function, that angle into a trig function, and get the value. Okay? So, modeling the length of a sag curve. When a highway goes downhill and then uphill, it has a sag curve. Sag curves are designed so that at night, headlights shine sufficiently far down the road to allow a safe stopping distance. See the figure here. Yeah, so I guess S is in feet. You have the width of the curve is in L. S is the length from the headlight on the car to where it shines. Okay. The minimum length L of a sag curve is determined by the height. So this is the minimum length of the sag curve. Is determined by the height of the car's headlights above the pavement. Okay. The downhill grade, so that the downhill angle, the uphill grade, and the safe stopping distance S for a given speed limit. In addition, L is dependent on the vertical alignment of the headlights. Headlights are usually pointed upward at a slight angle alpha above the horizontal of the car. Using these quantities for a 55 mile per hour speed limit, L can be modeled by this formula, where S is obviously less than L. And so, we're not getting into, don't get bogged down with the details of all this road design. This is not about road design. This isn't a road design class or anything, but the idea is the software or whatever, or I guess the designers need to be able to get, say, okay, you have an alpha is equal to this, and you need to just evaluate the tangent of that, right? And that's what the computers or the behind the scenes, the software is doing. It's doing an approximation for that. You just input an angle into this tangent and you get the value. Now, how this formula is designed, like where the tangent comes into play as far as the design, we're not going to get into that in this video. So, okay. Compute L to the nearest foot. If H is 1.9 feet, alpha here is alpha, theta 1, theta 2, and S is 336 feet. So I'm assuming like this theta 2 and theta 1, they are in degrees. Let me check that. Yeah, theta 1 and theta 2 are in degrees. Because let's say, we're going to learn about radians later, but let's say, it doesn't really, you need to know if, like, you can input any angle into like a trig function, and you could interconvert between radians and degrees. You just make sure you could, it doesn't matter as long as your calculator's in radian mode and you input that angle in radians, you get the trig function value. If that calculator is in degree mode and you have that angle in degrees, then you get the correct tangent value that way too. But when you've got angles outside of trig functions like this, then it's a little different. Like, you need to know what the units these are supposed to be, or else you're going to have to, it's going to change the whole formula. You see, that's something you'll learn as you go through school. So yeah, but theta 2 and theta 1 are in degrees. So, all right, L is equal to, you've got theta 2 is 4 minus theta 1. Okay, and then S is 336 squared. That's in feet. It specified that this was also in feet. We don't have to convert anything to convert to some other units. Okay, then 200, H is 1.9 plus S times tangent of 0.9 degrees. Okay, so this is 4 plus 3, that's 7. So 7 times 336 squared is 790,272. Okay, and then we've got, so tangent of 0.9 times 336 plus 1.9 times 200. And then what we can do is just go ahead and do the division here. So this divided by this. Okay, and they want it to the nearest foot. So we're going to round this decimal, so that's 550. So L is 550 feet. And that's based on these constraints, that's the curve width, or the curve length. Okay, repeat the previous exercise, but with alpha is equal to 1.5. So we're changing alpha from 0.9 to 1.5. What does that mean? So it's the alpha is like the spread of the lights. Okay, they don't tell us what alpha is. Or maybe it's the orientation of the lights. Oh, no. Headlights are usually pointed upward at a slight angle alpha above the horizontal of the car. Oh, okay, yeah. So it's a slight upward pointing of the headlights. You might say, well, why don't they just make the alpha really big? Well, it's probably, you don't want to do that because if you're traveling straight, it's you don't want the headlights pointing up too much, right? But I think they, some fancy cars, actually the headlights will adjust their angle. They'll detect this and adjust the angle, so that's pretty cool. But okay, so what we want to do is everything is the same except we're changing that alpha. And that alpha is where the tangent comes into play. So let's just write it out again. I don't want to. Okay, so L is equal to, so 4 minus 3 is, so that's theta 2 minus theta 1. Then S is 336. Then you've got 200, and then H is 1.9. Tangent, and now we're going from 0.9 to 1.5. And so we can think about this if we come back before we do the calculation. I imagine the L is going to be less, right? Because it's going to lower S because you're going to have, it's going to be, ideally, right now, ideally it would be pointing like this. So you can have the full range of the headlight. So we expect L to go down here. So, okay. You've got 4, so that's 7. So 336 squared times 7. Okay, then you've got tangent of 1.5 times 336 plus 1.9 times 200. And now we want to divide this divided by this. So 50, we're around here, 53 feet. 53, that can't be right. And here it was 550, so I've had to have made a mistake. 336 squared times 7. Oh, I see what happened. Okay. I divided. So this was multiplied by 200, got this. Now I want to divide this by this. 369 feet. Okay. So yeah, there's just that little bit of angle increase results in a kind of a large change in the required length of the curve.